we'll be solving discrete location problems. As part of that procedure, branch and bound, the first step is to solve a linear programming relaxation of the problem. And that can be done if you wanted to solve just a linear program using Matlab's linprog program for linear program. They do have an integer linear programming that we'll be using to solve the discrete problem, and the first step that it uses is to call the linear programming procedure to get a relaxation of the mathematical programming model. The arguments for the linear programming package, the set of arguments, and these are pretty much uniform throughout this and the discrete version of the problem. The first argument are the coefficients for the objective function, the C coefficients. Then you have two separate sets of constraints. The first are the less than or equal constraints, and A represents all of the coefficients of those. B is the right-hand side variables for those constraints. And then you have the equality constraints, and those are specified as a separate matrix. These are the right-hand sides of those. And then you have the lower bound and upper bound of the variables. There's actually a couple other input arguments. One, if you want to specify the initial starting solution, and different options. So this is an example that we talked about in class. So I'll just duplicate that to get the model. And then to solve linear programs, since the example is a maximization problem, we take the negative of the cost coefficients. And then we've found the optimal solution. Again, since it's a maximization, we get a negative result as our total cost, and we get two values. Both of those are not integer values, but they are the solution to the linear programming relaxation. Another way of calling the program is, instead of having to call it with multiple input arguments, sort of a nice trick in Matlab is to put it all into a cell array. These are the curly brackets. And in this case, since I'm going to be using no equality constraints, I can just put the empty array to represent, ignore or use the default value. So here I've defined a cell array, and then to see what the elements are, I basically can do curly brackets with a colon, and what I get are actually the 7 different input arguments, all returned as outputs. This is an example of what they call a comma-separated list. And by accessing the cell array this way, it's equivalent when I call it as an input argument to calling it with those 7 different input arguments. And with that, I get the same result. The reason to do this, to put it into a cell array, is to keep all of this information. Instead of having lots of separate arrays in your workspace, you can collapse it all into one cell array and then just call it in one step. So that's a nice convenience. To take the problem, then to actually solve it as an integer problem, we're going to define both of the variables x1 and x2 to be integers. And to do that, we want to use then to solve the int-lin program. And if you look at it, the format is pretty much the same as the linear program. The only difference is we have inserted a second input argument. And what it is an argument where we specify the indices of any variables that we want to be discrete integer variables. So in our example, we want the integer variables to be 1 and 2. I'm going to open up the documentation for int-lin program, and it's quite extensive. It gives a good example of all the different options. Here are the examples we'll be using down to this alternative, but there's other options, x0, where we can specify an initial feasible point. That would be useful if we want to use one of our heuristics to get a starting point. We can maybe eliminate part of the search in the branch and bound tree, so that can speed up our overall solution procedure. And then there's a series of different options. I think for our uses, we'll pretty much always use the default, but we might have some situations where we want to use one of the heuristics that we have to develop an initial starting point. So that might be the one option that would be important to look at. Then they have examples. A new thing in Matlab is called live scripts that show an example of how to use different things. So this is a quite extensive and useful documentation of all the options. Again, initially I wouldn't recommend getting into this, but just be aware it's there, that once you get comfortable using a program like this, and the same will hold true for Gurobi and a lot of the other packages, if you do need to get into more detail, Matlab does provide a quite nice documentation of everything you need to actually use the program in more than just the basic matter that we'll be using it in this class. The good news is that for most of our applications, we can use just the standard default and don't have to get into a lot of those types of detail. So I'm going to define the integer linear variables. And then I'm going to insert those as a second argument into the original LP cell array. I'm going to keep the first argument, insert the integer indices, and then the second through the end. The end is convenient because I don't have to know what the actual length of the cell array is. I'm just taking everything to the end. And then I can do the same thing of curly brackets with a colon to get all of those input arguments. I can then solve this, and I get now an integer result, and I get a maximum value of 30, which is less than the LP solution, but it is the best for the integer solution. So that's the first alternative, using MATLAB's intlin program directly. In the direct use of it, you basically have to create the arrays and then call the procedure. For large problems, that could be really inconvenient. The A matrix itself might have 1,000 rows and 1,000 columns, and each section of that array has a different structure because it corresponds to different variables in your math programming problem. So to make it a little bit easier to input, well, actually quite a bit easier to input models, there are a variety of different types of algebraic methods of creating a math programming model. Some of the better known are AMPL, A-M-P-L. That's available for Gurobi, for Cplex, and for a lot of mixed integer linear programming solvers. They provide more of an algebraic interface. In MATLAB, there's not a direct implementation of AMPL. So in MATLAB, there is something that gives you some of the same capabilities, and it's called the MILP object with a capital M. And what it does is it allows you to input models more algebraically, and that can help in the creation of the model. Before this was available in MATLAB, it was really quite difficult and required quite an extensive amount of basic MATLAB programming and array manipulation to create the inputs. So with this formulation, it really simplifies it quite a bit. So for that example problem, first we can look at the documentation for MILP, and you can see these are all the different things that you can do in terms of methods that operate on this object. The ones that we'll be using, all of the add ones create the model. And then at the end, we can display the resulting model. And then at the bottom are all the different conversions. So we can take a standard linear program from MATLAB and convert it into an MILP object using LP2 MILP. We can go the other direction. And then we can also convert the MILP into a Gurobi object. And that's what we'll be using as our solver. The object actually created by MILP can be used directly by Cplex. So we don't need to convert it from MILP to Cplex because it's already designed. It was originally designed to operate in Cplex. So the MILP to Gurobi was added later when we switched from using Cplex to Gurobi. And then there's examples. This portion here illustrates some of the different syntax options. So it's not actually solving a real problem. It's just to give you an idea of what are the different syntax for creating constraints that has the most variety. And then it shows here by displaying the model, you can see what the overall results are. And then the second example is a UFL solution, and this is the same one that we'll be talking about shortly. And this is presented in the help information for the MILP, because I think the UFL problem is really the best illustration of the use of this MILP object, even though using a heuristic is probably the best way to actually solve the problem. But I think it's a really good way to actually learn the syntax aspects of using MILP. So the first thing is, every time with this object, if we want to keep reusing it, we're going to always want to be clearing it. In this case, it doesn't exist, but it doesn't hurt to go ahead and say just clear in case we had previously created an object. If we didn't do that, every time we added constraints, it would add it to the existing object. So we'd get a model that is not really what we intend. So in this case, we're going to be clearing it as a matter of course. And then the first step is to just assign an instance of that object. And you can see it's created it, and it's called an MILP. So if you look at over here in your workspace, MP, and then look over, its class is actually MILP. So it's defined as a unique object. And then to see what the model is, that's the one structure that it has. It basically has empty information or default values for all of the different elements of the model. The only one that is specified by default is MILP. And then the first step is to create the objective function value for the model. And in this case, we can specify the sense of the model as a maximization problem. And then we just give it the array corresponding to the objective function elements. For more complicated models, we can specify multiple arrays. And that's where the real power of the algebraic approach comes into play. In this example, since it's so simple, it's not going to seem like it's much different than just directly creating it. But once you get comfortable with the syntax, and then we get to the more complicated UFL example, you can see some of the benefits of this approach. So I've added that, and if I want to see what's been created, I can just look at the model again. And what's happened now is it's, again, kept the MILP name, but now it knows the sense of the model. It knows the coefficients of the objective function. It's put default lower and upper bound. The defaults are 0 and infinity. And by default, the type of variable is continuous, and later we'll specify it to be integer. And then for the constraint matrix, it knows that it has to be, since we have two variables here, we know it has to at least be a 2 by 0 empty matrix, but we haven't specified any of the constraints yet. And then we also haven't specified left and right hand side values. So it's basically put as much default information as possible at this point. And now we can specify the constraints for the model. And then I can look at the model again. And now it's actually then created the A matrix. And it also was able to create the left-hand and the right-hand side. The MILP object uses the Cplex way of specifying a math programming model. So again, if you look at the slide, you can see that compared to Gurobi and Matlab, it uses a left-hand side and a right-hand side, as opposed to having to, in the case of Matlab, it separates the less than and equality constraints. And in the case of Gurobi, you actually input the sign of the constraint, greater than, less than, or equal. So Cplex is an alternate where you specify a left and a right-hand side. In terms of implementation, is I think actually a little bit easier in terms of developing the code for the MILP to do the left-hand and right-hand side. And originally it was designed just for Cplex. So I've basically kept that formulation and then converted into Gurobi if you want to solve it using Gurobi. Next, I'm going to add the constraint that the integers have, the variables have to be integers. And all that's done is added the C type to be integer. And notice that I specified it's just a single I, but since my model has two variables, it is duplicated it twice. And that's something that is required by Cplex, and it's also required by Gurobi. You basically have to have a character string where each character corresponds to one of the variables. And you can imagine if you had, 10,000 variables, you have basically a character string of 10,000, and the character corresponds to, C if it's continuous, I if it's an integer, and B if it's a binary variable. And then there's a method where we can display the model, and this is useful for small models. For larger ones, we want to use the SPY command. And then in this case, what I want to do is take that model and convert it into my integer linear programming formulation that I can then use to call and solve using MATLAB's intlin prog. So I use the method that converts MILP to a integer linear programming input. And again, this is just the 8-element cell array that I want to then pass to intlinprog using the curly brackets and colon. And then I can solve. I get the same result that I got previously. And then there's another method called name solution. And what name solution does is it comes into play when I have more than one array specifying the objective function. And it separates the resulting values into the corresponding elements of each of the original coefficient variables. So for this example, it's not going to provide a lot of benefit. The only thing it has done is that when I specified the objective, the variable I passed was the variable that I had named C. So the object actually sees that and keeps a record that that variable's name is C. So when I call this name solution, it's able to take the result and put it as a field in a result structure. So it has the value C there. So this becomes handy when we have lots of separate elements of our objective function, lots of different variables that we're solving. The solution is nicely partitioned into these different elements. Without that, the X variable itself would just be, an array of sometimes thousands of different variables, a single vector of thousands of variables. Looking at it doesn't give you really any insight. So doing this conversion into the corresponding elements of the original input objective, it really is convenient in terms of being able to process the output. And then finally, we have the objective function value returned. Again, since Max, the intlin program for Matlab doesn't recognize the sense in terms of a character, when it sees a maximum, when it does the conversion, it converts that into a negative of the coefficient, so that when we solve it, we get a negative result because this is a maximization problem. We could also use Gurobi. And before using Gurobi, you should go to the link on the course webpage, download Gurobi. As a student, as long as you access it from a .edu educational environment and have a .edu email, you can get an educational version of the full version of Gurobi, and it's valid for 1 year. And then as long as you're a student, you can renew it. Just a few days ago, I guess I had originally downloaded Gurobi about a year ago, and I had to renew my license, and it was easy just to, basically just executing one command, it updated it, so I should be good for another year using Gurobi. This is documentation for Gurobi, and this is documentation for the Matlab interface with Gurobi. There's also a Gurobi interface for Python. The Python interface is more extensive than the one for Matlab, so if you're going to be using Gurobi extensively, you could use Ample, which is the algebraic language. But I think it's, once you've taken this course and learned Matlab, it's probably more convenient to actually switch to Python and then use Python to interface with Gurobi, since Python is the more common package used for scripting compared to Matlab, at least for a lot of the applications that would use mixed integer linear programming. It's probably the recommended conversion step. Again, it's, I think, nice to look at the Matlab first because it's an easier first step. But once you're comfortable with this, then you could, I think, very easily switch over to using the Python version. A lot of the syntax and stuff would be very similar. And I'm not sure if there is a MILP type package available in Python, but I would assume that if not, there would be one at some point. So in terms of solving for Gurobi, so that's the help information. First, I'm going to clear out model and parameters, again, because if I want to keep reusing this code, since the calls are very structured, it's quite common that I'm using the same set of code of lines in a cell repeatedly. So it's a good idea to include a clear there just to eliminate potentially any errors. And there are ones that wouldn't show up as an error, but you would get wrong results. And those can be some of the most insidious types of errors. So I'm going to clear the parameters. And then for the model, I'm just going to create a model. And all this is a structure. So it has very similar components to calling the MILP object. So I'm just going to go ahead and execute all of those. And then when I finish, I have a regular Matlab structure. One constraint is that when I specify the A matrix, and I'm just using the values of the A matrix that I had previously specified up here. so I'm not changing anything. For Gurobi and using the Matlab interface, the A has to be a sparse matrix. So I can take A, which is a regular full matrix, and just call sparse, and that converts it to sparse when I add it to my model. And now that it's part of the model, I want to set the parameters. I want the output flag to be 1, and all that does is it displays the results as it solves the model. And then when I call Gurobi, it's just a regular Matlab function Gurobi. That's a wrapper that then calls Gurobi. And then once you install Gurobi, you should see on your computer, when you look at the different programs installed, you should see a actual command line version of Gurobi and several other alternative ways of using Gurobi. The Matlab version of it is accessed by adding to your path command. So if you look at, if I do edit, startup, it'll open my startup command. And you can see that as part of my startup command, I do have a link to Cplex, but then I also have a path to where I have installed Gurobi on my machine. And there's a folder within the Windows thing that's called Matlab. And you also see a Python folder. So if you do want to use it in Python, you can do a similar thing. So all I've done here is added a path. So just like you access Matlog by adding a path, you can add this path so you access Gurobi. So once you've done that, then when you call Gurobi, you'll know up here if you do doc and Gurobi, and if it can't find it, it'll give you an error when you try to look at the documentation. So in my case, I know Gurobi is working, so I can go ahead and solve it. You can see the results here again because I set the output flag to 1. It shows all the intermediate results. You can turn that off if you're going to be solving problems and don't want to see that. Then the results themselves are specified, and what we're interested in is the objective value of 30. So this is our TC value, and then X are the coefficient values, but it also gives you slack, bound information, runtime, iteration counts. In this case, it didn't have to do any, but it gives you more information than you're typically interested in. So here I'm going to just relabel that so I have my X result, and then TC is my total cost. In this case, notice that it's positive. It doesn't return as a negative, and the reason is that Gurobi recognizes the maximization sense, so it returns a value that is doesn't have to have the negative there. And that's so this example is calling Gurobi directly. As an alternative, since we've already specified the MILP object, we can, and I'm going to clear the parameters. Again, that's just something that is good to do every time before calling Gurobi. Then what I'm going to do is use the conversion function MILP to Gurobi for my math programming instance that I've created. And when I do that, it automatically converts the mixed integer linear programming model into a Gurobi instance. So at this point, I can do everything just like I did previously. Notice the only difference here is in terms of the result. Instead of just assigning result.x to x, I can use the name solution capability of the MILP object, and then take that result and assign it to the structure where I know that the corresponding coefficients are in the array C. Again, for the small example, it doesn't really add much, but for the larger ones, this starts to become convenient. The next example is to solve the UFL problem, and this is the same example that is given in the help information for the MILP object. And for this, again, I'm going to clear everything, including my previous MP object, so my entire workspace gets cleared out. Here I'm going to specify a column vector. Again, it's column because of the transpose. These are my fixed cost, and then a 6 by 6 variable cost C array. So these are my two input variables, the C matrix and the K vector. And then I can solve it, in this case, just using the hybrid heuristic. And I get a solution, 3 and 6, for a total cost of 31. So remember that as a reference. And then this is an example of, and what I label this as reusable UFL code. So anytime I want to solve a UFL math programming implementation, it has basically the same structure. So I can basically just change the input variables, the C matrix and the fixed cost, and then everything else I can basically derive as needed for my UFL model. So this is a cell that I can keep reusing as I solve different instances of the UFL problem. So again, in this reusable code, I'm going to clear any previous MP. I haven't created anything, so there's nothing to delete, but it's, again, good to do that in general. Here I'm going to call my model UFL. So instead of just MILP, it's named it as UFL. That way, if I've created multiple objects, instances, I can look at the name and see which type of problem they refer to. I can get the values for n and m by just taking the size of my C array. And then here what I'm going to do is, since in a lot of problems I have constant fixed cost, it's useful just to specify a single scalar for the fixed cost. But then when I create my math programming implementation of the UFL problem, I do want to indicate exactly how many potential new facility sites that I have. If I did just a single scalar k, it would basically just have a single variable or a single site, and that doesn't make sense. I do want to have a total of n. So what I'm doing here is I'm using the replicate matrix command, and I'm using the IFF. So if my input k is a scalar, then I replicate that scalar n times. If not, then I just force it into being a row vector. So the IFF then is used to create an extended version called kn. So if I look over here, my original k was a 6x1 column vector, and all it's done is, since this wasn't a scalar, it's just converted into a row vector. If I'd had a single fixed cost, then it would have made 5 more copies of that same fixed cost. And then at this point, I can create my objective function value. The total number of variables in this model is n for the yi variables, and then n times m for the xij variables. So in this case, it's the 6 plus 36 for a total of 32. To add constraints, you're basically going to be putting into a for loop for each of the m constraints corresponding to the existing facilities, the constraint that the sum over I of all the xi's has to equal 1. So within the MILP object, you use the syntax first that in terms of the model that was created, there are 2 arrays with coefficients in the objective function. The first are the fixed cost, and then the second are the variable costs that are a matrix. So for this constraint, since there's zeros for all of the fixed cost, you can specify it as just a single 0, and that'll assign 0 to all of the fixed cost coefficients in the objective, in this constraint. And then for the xij values, since the xij's are just by themselves, they're not multiplied by any value, you can think of the value that they're being multiplied by as 1. So whenever it's 1, you can specify that you want to take the sum of, in this case, an entire column of the C matrix or the xij matrix. Given the formulation of the UFL problem, the first set of constraints are separate constraints for each element of M, representing the existing facility locations. So in terms of adding the constraints, we put those into a for loop. And then the index j is going to be from 1 to m, existing facility sites. And then the constraint itself is added. Each row of the constraint matrix is added as one call to the add constraint method. And then since the fixed costs are all 0 in this case, we can specify 0 by just putting a single 0 value. And what that does is assign the coefficient of 0 to all of the yi variables for that row of the constraints. And then for the other portion of the row of the constraints corresponding to the xij variables that are to which the coefficients of the C matrix are applied, since the value is 1, we can specify in this case that we want to take a sum over an entire column of the xij's by using the Matlab-like notation of a colon. So here we just create the string colon, and that tells us that we want to sum over the entire column of xij's, and then we want to take a particular column, the j column, and for that then we wanted to assign it to be exactly equal to 1. So essentially over here, what this is saying is we're summing over the elements of xij to equal 1. So that is a means of actually then implementing this set of constraints. We do a similar thing for the other sets of constraints, and in this case these are applied to the elements corresponding to the potential new facility sites. There's a total of n of those, and for those the constraint that we'll be implementing is to multiply m times yi. This is an example of the weak formulation. And what we're then comparing it to is the sum over all existing facility locations j, the elements of xij. And since these elements are going to be between 0 and 1, even if all of the existing facilities were assigned to a particular new facility, the maximum summation would equal m. So as long as yi, which is going to be a binary variable, taking values of 0 or 1, in order for this constraint to be satisfied, if all of the existing facilities are to be assigned to a particular site, then for this constraint to be feasible, the sum here will be equal to m, and then we have m times yi. Yi would then be forced to have a value of 1. A value of 0 would force this constraint not to be satisfied, so that would never occur. So these constraints are the ones that force new facilities to be established at sites to satisfy this constraint. We can implement that then. In this case, we're using a slightly different version of the notation. And in this case, instead of specifying a colon, which says to take an entire row or column of a matrix, here we're just specifying the scalar m and applying it to m times yi. So this use of the notation, we have the cell notation nested twice. We have the original cell notation, which is right here. And in this case, since yi is a vector as opposed to a matrix, there's just one element. So that's the I element. And then we're applying a second cell array to this index cell array. And that second element, then we can include as a first element the non-1 values of the coefficient. So in the previous case, since the value was 1, we didn't need to do this step. But in this case, since m is not necessarily equal to 1, we want to explicitly include that. So that's how we get the m times yi variable. And then for this part, since we want to sum over the j elements and do that for each row I, we can specify it here by putting the colon in the second position and then indexing over I, which is in this for loop. So that allows us to add these constraints, and then the only thing left to do are the upper and lower bounds. In this case, upper bounds of 1 for both y and xij. In terms of the constraint types, I'm only going to restrict the yi's to be binary. I'm going to let the xij's stay as continuous. And in the case of the uncapacitated facility location problem, the results will be always either 0 or 1. It never makes sense to split part of the demand. You should always just put it at the lowest cost alternative since there's no capacity constraints. There are versions of the problem where the facilities have a maximum capacity. In that case, a portion of the demand would be served by that facility, but then once capacity is reached, another portion could be served by another facility. So in that case, the XIJs could have values less than 1 and have a continuous value. So it turns out we can keep them continuous, which makes the optimization problem easier to solve. It reduces the size of the branch and bound tree because it only needs to branch over the YI variables as opposed to the YIs plus the XIJs. So this is a formulation detail that makes the solution procedure much quicker. If we set it to B, then it would still solve and get the same answer, but for large problems it would take significantly longer. So I can execute that. And then finally, for this problem, we can look at what is the corresponding model. Here you notice that for all the variables, there's 6 YI variables and 36 XIJs. These are all specified as the characters capital C for continuous. These 6 are capital B for binary. The size of our constraint matrix is 12 times 42. Likewise, the left and right hand sides are 12 elements because we have 12 constraints. And then the variables, we have 42 variables, so the upper and lower bounds are 42, and our objective value is 42, which is the Y plus the XIJ variables. We can display the model since it's small. We get this result. Even for this small of a problem, you can see the mixed integer linear programming formulation is quite extensive. And as I was mentioning earlier about the difficulty of creating this directly in Matlab, you can see here that you'd basically have to write Matlab code to create an A matrix that would have this structure. And if you look at it, it's something that at least I would characterize it as being non-trivial. There is structure to it. These are all 1s for the first 6 constraints. So the first 6 constraints have a pattern of 1s, and then over here there's a value of 1 in the first row of the constraint, values of 1 in the second row, and so on. So the pattern itself is rather complicated to generate. And likewise for the second set of constraints, there's another fairly complicated pattern. So by using the MILP object, you can do it in a format. And if you look over here, this format I think is much closer to the mathematical formulation of the mixed integer linear programming problem for UFL. So it's much more of a one-to-one mapping. And now that we've created this, we could do like we did before. We can solve it using the Matlab's intln-prog. And if we do that, we get this result. And then instead of immediately displaying the result, I provided a second alternative to use Gurobi. And then in both cases, we can take the results and then have a single cell here to actually display the results. So in both cases, either with Gurobi or with Matlab's intln-prog, I'm going to take the result and then call name solution. When I do that, you can see now that it's separated the solution variables in the optimal solution into 2 categories. The first are the fixed cost coefficients, and this then tells us which locations are we establishing new facilities, in this case 3 and 6. And then it groups together all of the variables of the C matrix as a 6 by 6. Total cost is again 31. We can take the results of this solution and then actually solve. So I'm taking the elements of the solution vector as a structure, and I'm taking the Ki coefficients, and I'm also taking the Xij coefficients of the C matrix, and I can then do a direct calculation and get the same total cost. Notice in this case, the reason for the zeros here is that this is numerically not exactly equal to 31. And then here, if I want to get the actual indices of the new facilities, I can use the find command, which returns 3 and 6. And then the number of new facilities, I can just sum, and there's a total of 2 new facilities. So this is a display of the information returned by a UFL problem, and this is meant to be generic. So we can take, in this case, we're solving this particular instance, but we can take the same set of reusable code and then apply it to other problems. The next example, I'll be creating a mixed integer linear programming model of the p-median problem, and I'm going to use the same data from the previous example. And the main data is the fixed cost, the C. So I can solve it first using the p-median heuristic, and I get a solution where my total cost is equal to 8, which is just the sum of the variable cost. And then the 3 sites selected are 2, 3, and 5. And then I'm going to be using my reusable code. And I can use it since the UFL problem is so similar. It's just basically an additional constraint added to force P facilities. And then the fixed cost coefficients are just equal to 0. So if I set K equal to 0, I can go back up into my fixed cost. And here I'm using the fact that if it's scalar, I'm going to replicate it. So I'll have a zeros for all of my fixed cost coefficients. Here I'm just going to execute this entire cell. And then after executing this entire cell, this comes back as a UFL instance. So I want to rename it to be p-median. And then I just add that one additional constraint. The sum over all of the yi's has to equal 3. There's nothing involving the xij's, so I just put 0. So I'm adding that constraint. And then I can display the model. And here everything is the same as the UFL, except that I have zeros as the coefficients for the yi's. And then I've added this 13th constraint that has 1s for all of the yi variables and zeros for everything else. And in terms of the left and right-hand side, the right-hand side is 3. The left-hand side is 3. And that's the way of specifying equality constraints to have equal left and right-hand side. That was started in Cplex, and it's also in the MILP object. And I think it's a nice, easy way of doing that as opposed to processing just the equality or equal sign. This is our resulting model. Again, very similar to the UFL formulation. And now that we have the model, we can solve it using either Matlab or Gurobi. If I want to use Matlab, I get this solution. I'm going to skip Gurobi, go to display solution. I get the same result. And the same sites are chosen as previously. If we go back up to here using the heuristic, we got 2, 3, and 5 for a cost of 8. Here we got actually 2, 4, and 6, the same 3 facilities, and the cost of the same 8. So in this case, we actually have different sites chosen, but the overall total cost is the same. So it's essentially identical solutions. Another example, example 4, again, we can reuse our same code, but in this case, we're going to create new data. So this is a larger problem, and I'm going to get a total of 104 sites for existing facilities, and then use those also for potential locations for my new facility. So I'm going to start with first clearing everything from the workspace, and then I'm going to take the 5-digit zips in North Carolina, and to get a lesser number of points, I'm going to restrict them so they're zip codes that only have populations of at least 30,000. Again, this would not be good in practice to eliminate everything below that. It would be better to aggregate and include the populations below that into a larger combination centroid, doing something closer to the 3-digit zips. So this is just done for convenience to get this set of points. But in practice, you wouldn't want to, pick such a high threshold for these zip codes. You'd be better off actually aggregating all of the zip codes such that you got to a number of 104, if that's your target size. So this is done just for this example. So I get the set of data, assign it, location, area. Again, this is aggregate demand data. So I want to use the area adjustment for my distance calculation. So with this, I get a 104 by 104 distance matrix. Population is going to be my demand. My transportation rate is going to be $1 per 10,000 population. So that's just 1 over 10,000 as my rate. Again, these numbers don't mean anything. They're just for example purposes. I can create my variable cost. It's just the product of the transport rate times the distance times the demand. Everything cancels except for dollars. I'm just going to pick 500 as an arbitrary cost, and that'll have to be then replicated in my reusable code. For the UFL heuristic, it has logic in it that if I have just a single scalar, it'll expand it and assume that that value is the same. And when I solve it, then I can use first the hybrid UFL heuristic. And I solve it. And here you can see it actually went through 2 iterations, got down to a total of 10 site locations and 10 new facilities, and 1.21 is our cost. Here I can plot the solutions. And these are all the zip codes, and you can see that these are the locations then of the 10 sites that are established that minimize the total person miles traveled. Again, a classic type of location problem. If we want to then solve it as a mixed integer linear program, we basically have all the data we need. So at this point, instead, before we can do a comparison, if we go back up to the reusable portion of the code, we've just re-executed this. Notice now this is a much larger model. We have almost 11,000 variables. So this is more of what you would see in practice. So much larger model. This one we don't want to display. If we spy, the result we get here is a very large model. And zoom in, you can see again that sort of classic UFL structure. We can zoom in. And this is what our overall model looks like. Then we can solve it using either of the two. This one's larger, so I'm going to use Gurobi. These are all the steps of the branch and bound tree. This is our displayed solution. In this case, it got a total of 8 instead of 10. And this is, it looks very close to what the total cost is. Here I'm displaying both the result returned by Gurobi and then explicitly calculating using the results. They should be the same number. Then I can take that, go back down to the last cell of this example, and I then do a comparison. So first I'm going to compare the number of new facilities, 8 versus 10 for the heuristic, and then looking at what the difference in objective function value is. What it's saying here is it's just about a 0.5% difference. So by modeling as a mixed integer linear programming, I got about a 0.5% improvement compared to heuristic. For this larger problem, again, that illustrates that for most practical problems, just using the heuristic for this problem is really more than adequate. 0.5% is really nothing that would make it worth to actually do a MILP formulation unless you had additional things you needed to do to make the model such that the basic simple heuristic would not be feasible for this problem. Otherwise, you wouldn't want to use MILP. The next example is another UFL solution. And for this one, what I'm going to do is load the data that I created from our previous video for the POPCO example. So first I'm going to clear everything out of my workspace. Then I'm just going to be loading the POPCO data. And what I get are the 203 by 161 variable cost. And then I have my single fixed cost. Remember, that was the y-intercept of the linear regression. And then S actually represents the original data that I had read in from the spreadsheet. The reason I say that is that I may want to then modify it, not for this example, but for other uses of the POPCO data. So the first step is to solve it using the heuristic. There I get 23 with a cost of 7.09. And again, just like I did before, I can go back to my reusable code up here, get my reusable code. I won't just spy it. This is even a large problem also. Solve it. Go ahead and use Gurobi. Let's go ahead and use linprog also. You can see it's still solving. It looks like it took a little bit longer. Displaying the result. We got a total of 22 new facilities, and this is the total cost. The last part of this example then is to compare. Results, we got number of new facilities, and then the difference here is only 0.25%. So again, the mixed integer linear programming is only providing a 0.25% improvement. Something probably not really worth bothering with in practice. The next example is to look at MILP formulation of the set covering and the set packing problem. And for this, I want to clear all my variables. And also, if I have any figures open, I can do close all, and that gets rid of the figures also. And for this problem, looking at the slide showing the different sets and objects, I have a total of 6 objects. So the A matrix has 6 rows in it, and I have 5 sets. So the A matrix has 5 columns in it. And then 1s indicate for each subset which objects are contained. So I can directly just take my A, and then for the cost, I'm going to set them all equal to 1. So at this point, yeah, I'm not going to be using the UFL recyclable code because this is a different problem. So here I'm going to directly create the solution. Here is the, that's the name of it. Here I just have the cost of 1 for each subset added. The constraints here are just a single call. It's basically my A matrix, which is a 6 by 5. That will directly create all of my constraints because the structure up here already represents what my constraints need to be. Basically, I'm saying that the sum of each row of this A matrix has to be greater than or equal to 1. So in this case, the structure is already created by specifying the subsets. Everything is binary, and then I can display what the model is. And then I can solve it, and here, when I solve it, the objective is just the indices corresponding to where I actually have sets that cover all of my objects. So in this case, sets 2 and 4 cover all of them, and they're the minimum number of sets that cover all 6 objects. The dual of the set covering is the set packing problem. And here the objective is not necessarily to cover every object, but to maximize the number of subsets that are mutually pairwise disjoint. So for this problem, I'm going to clear my previous object and then set that equal to set packing. Here it's a maximization since it's a dual of the set covering, which was a minimization. And then my constraints are less than or equal to 1 for the A matrix. Again, it's binary. I can display the results. Solve it. Here the indices are J, and they correspond to the 3 subsets that are the maximum number of subsets. So 3 is the maximum number that I can have covering the 6 objects such that they don't intersect with each other. And again, as mentioned in class, the set packing problem itself is not one that has a lot of logistics engineering applications. The next example is a set covering problem, but using it in the context of a location problem. So here I want to find the minimum number of North Carolina cities from which other cities are within 50 miles. So imagine almost like a relay tower. From each city, you want to be able to reach another city within a 50-mile radius. So I'm going to close all the variables, any figures, create my NC city data. Here, I'm just going to use circuity factor of 1.2. There's no notion of area adjustments. I'm going to assume that every city is far enough away that that doesn't come into play. And then I'm going to set the A matrix originally just to false and make it into a logical vector. In this case, 84 by 84. 84 corresponds to the number of cities. And then I can very quickly and easily in one step create my A matrix by just setting the elements of my distance matrix that are less than 50 miles equal to true, and then everything else is going to remain false since that's what it was set originally. So I can very quickly set my A matrix. My C's are all going to equal 1. And again, I need to explicitly create the size of the C matrix so that the mixed integer linear programming model actually has the appropriate number of variables. And then here, I'm starting to create my object. It's a minimization. Again, the same type of set covering formulation. When I display the model using the SPY command, you can see the A matrix. All of the blue colored elements of this matrix are the true values of the A matrix, or the 1 values of the A matrix that correspond to cities that are within 50 miles of each row of this matrix. We can solve this. Here I can use the Matlab integer linear program. We get a total of 11. Can also solve it using Gurobi, get the same result. And then finally we can plot the results. And we get this set of cities corresponding to the ones that are within a 50-mile radius. Again, this is different than the UFL problem. The problem was to try to minimize total people miles. Here it's a different type of location problem. Here the only objective is to try to minimize the number of cities selected such that all of the other cities, all of the other red dots, are no further than 50 miles away. That illustrates, for example, why Elizabeth City is chosen, because it's probably greater than 50 miles of any of the other cities. So we have to establish a facility there just because of that constraint. If we were trying to minimize total people miles, we could afford to not establish the facility there, since it has probably, in terms of population, a very low population. But population doesn't factor into this problem. It's just a matter of distance. So we get a completely different type of solution. In terms of logistics engineering, that type of thing does come into play quite a bit, particularly because of, in the case of trucking, there are limitations on maximum distances that can be traveled in a day. So as a set covering problem, you can locate, for example, different terminals for trucking solutions. So this is a type of problem that has much more extensive logistics engineering application than the set packing problem. And then finally, another problem that we're not going to be talking about directly in class, but I wanted to include the mixed integer linear programming solution of it, just so that you can compare this to the slide presented for bin packing, and to get a little bit better idea of what are some of the syntax issues involved. So for this problem, we have a total of 20 objects, and we'd like to put them into the minimum number of bins, subject to each bin being able to hold a capacity of 10. And the capacity then is in terms of the volume units. So for this problem, we have 20 objects. M equals 1 to M is going to be the objects to be packed. And then our bins, capital V, represents the volume of each bin. So it can hold a maximum of 10. And then to get our individual volumes for our objects, I'm just going to use a random integer between 1 and 5. So this gives me values between 1 and 5 for all 20 of the objects. And then the subset sum of those cannot exceed 10 corresponding. So these could be the pounds of each object. And each bin then can have a maximum of 10 pounds. Or it could be the actual cubic volume. And then this would be the cubic volume of the individual objects. And then 10 would be the cubic volume of the bin. To formulate this as a mixed integer linear program, first I'm going to name it. And then in this case, I'm going to define all of my coefficients for the first variable, which are my yi's, as 1, because I'm trying to minimize the number of bins. So instead of explicitly assigning this to a variable, I'm just going to do the calculation and creation of the 1 vector directly as an input argument. And then for the xij's, they don't appear in the objective function, so they'll have 0 coefficients. And here I'm going to do a 20 by 20 matrix of zeros, which is just zeros with a single input argument of m, which is equal to 20. So all of that then creates my objective function. I can then create the first set of constraints. And just like the UFL problem, this first set of constraints ensures that any object assigned to a bin that's established, the product of the volume of the object, V, times 0, 1, indicating whether or not it's in that particular bin, the sum of all of those cannot exceed the volume V of the bin itself. So this is the object volume. This is the bin volume. Here it's indicating that we're doing a summation over all of the objects. And then I equal M is for each of the bins. So we start off essentially with a maximum of 20 bins. We could always put one object in one bin and get a solution. It would not be a feasible problem if one of the objects had a volume exceeding the bin capacity. So we'll assume that all of the objects have less than or equal to the bin capacity. So here then I'm going to add this set of constraints. I can add the second set of constraints, which basically just say that each object has to be assigned to one bin. Here the yi's don't appear in this objective, so this is equal to 0. And here all I'm doing is summing over each column of the xij variables and assigning them exactly equal to 1. So I can execute all of those. And then finally the type is binary. And then if I use the integer linear program in Matlab to solve, I can solve it and I get this solution. Here I'm using the name solution to convert it. And then to actually see what objects are in each bin, I'm using a Matlab function called array function. And this is something you'll be seeing a lot. It basically allows you to specify a function handle as a first argument, and that tells you then how you want to process each element of an array. So in this case, what I'm doing is applying the find command, and I'm applying it to each row of argument 2. So if I look at what is the x return, since up here in the objective I didn't specify a variable, I just did a direct calculation of the values. It doesn't have a variable to assign, so by default it just says arg1, arg2 for however many arrays are specified in the objective function. And then for that, it's giving me ones here corresponding to the bins that actually are built. So we have a maximum of 20 potential bins, and we're selecting 6 of those to actually put objects in. So the remaining 14 are not utilized. And then the array function then is finding what are the non-zero elements corresponding to the indices of the objects in each bin. And it's then doing that for each of the arguments in the bin. So here I'm doing a find over the non-zero elements of the yi variables, which give me the indices that I want to iterate over. And then the remaining portion of this is actually argument 2. This corresponds to the 20 by 20 xij variables. And here I'm looking at what are the non-zero variables of each row I of the second argument, the 20 by 20 matrix. So applying all of that, I end up with a 6-element cell array. So B itself has a total of 6 elements, and then each element indicates the indices of the objects in that bin. So a cell array then is a nice, easy way of representing the results. Again, taking advantage of the fact that the length of the elements in a cell array don't have to be identical. So it's a nice way of very concisely representing and presenting these results. And then finally, this step is where I actually show the objects in each bin.